introduction to Bayesian statistics. This is Moose the dog. I think that Moose might be a genius. You can probably see why, but let's find out. Today we're going to do some tests on Moose. This chart represents my prior beliefs about the smartness of Moose. We're going to administer some IQ tests that I found on the internet to Moose. This is something Moose really likes. We cleverly hide the meat under a Detroit Red Wings blanket. A smart dog should be able to find the meat and retrieve it from under the blanket right away.
Okay, get the meat. Here. Get the meat. Okay, get the meat. Where is it?
Okay, let's try something else.
Look, there's meat. But look, wait. The meat goes under the cup. Wait, where did it go? Moose, where's the meat treat? Where did it go? The meat? Where's the meat?
Based on that experiment, we can modify our chart.
That's a little introduction to the world of Bayesian statistics. We had some prior beliefs, we collected some data, and we modified our prior beliefs based on that data. Let's talk a little bit more about the details.
This is an introduction to Bayesian statistical analysis. As you all know, Porky Pig is a Bayesian, and Porky wants to know about his origins. In particular, he wants to know whether his closest living relative is the Red River hog, or a different species of pig. Since Porky is a Bayesian, he approaches this problem with his question, but also some prior beliefs. He then collects some data that he can use to address this question. It's the combination of Porky's prior beliefs and the information in the data that will give him his results. And this is the basic structure of a Bayesian analysis. Prior beliefs combined with information in the data gives us our posterior distribution, which represents our results. Put in more statistical terms, we might be interested in some parameter theta, plotted here. Going into the analysis, we might know very little about the value of theta. For example, maybe we only know that theta could be anywhere between 0 and 1. We could represent this lack of knowledge as a uniform distribution between 0 and 1. This is our prior belief about the parameter value, theta. Information in the data then modifies what we think about theta. This updated belief, influenced by the information in the data, will be our posterior distribution. In this example, we can be quite confident that theta is somewhere in between 0.4 and 0.6 based on the information in our data. This is our posterior distribution. So we have our prior beliefs influenced by our data giving us our results. We can see the structure in Bayes' theorem, which is the centerpiece of any Bayesian analysis. Bayes' theorem is made up of several parts. We have this term, probability of the data given the hypothesis. This might look familiar to you because it is the formula for the likelihood. We have this term, which is the probability of the hypothesis. Notice that this is the probability of the hypothesis without any other information in the term. In other words, this is the prior, the probability we assign to the hypothesis before we even look at our data. And then we have the probability of the hypothesis given the data. This is the results. This is what we want to know. We also have this funny term down here, probability of D, which represents the probability of the data averaged over all possible hypotheses and parameter values. This term is really hard to calculate and is often constant for most Bayesian analyses. We can see how this Bayes formula relates to our previous diagram, the prior beliefs, the influence of the data via the likelihood, and the results, which is the posterior distribution. In other words, we take the prior, multiply it by the likelihood, divide by some term which is often constant, and we get our posterior distribution. Let's go back to our Mythbusters toast dropping example and see how that example works in a Bayesian framework. Remember, when the Mythbusters dropped the toast off the roof, the toast landed butter side up 29 times and butter side down 19 times. We first have to start with our prior beliefs about toast flipping. And in particular, what we're thinking about is our model parameter p, which we denoted as the probability of the toast landing butter side up. One obvious choice for a prior here would be a uniform distribution between 0 and 1. This prior is basically saying that the probability of toast landing butter side up could be any number between 0 and 1, and we don't have any way of favoring any of those hypotheses over any other, so we start out with a uniform distribution. Other choices are possible, so we could use, for example, a normal prior bounded between 0 and 1, or something like a bounded exponential distribution. We might use those if we have some other information about the toast. For example, maybe we flipped other pieces of toast and gotten an estimated p to be within some range most of the time, or we have some other reason to have a prior belief. The more information in the data, the less influence the prior has. And so if there really is a lot of information about the model parameter in your data, the prior will have a very small impact on your analysis. In general, though, in Bayesian statistics, it's good to try a range of different priors to make sure that you understand where your posterior distribution is coming from, whether it's being influenced by the prior distribution or almost all the information is coming from the data.
I want to pause for a second here just to talk about what some people refer to as uninformative priors. The term uninformative prior is used to sometimes imply a prior distribution that has no knowledge about the parameter of interest. In Bayesian statistics, you have to have a prior, and that prior will have some influence on your analysis. It's supposed to. That's how we get our posterior distribution. Our prior beliefs are influenced by the data to give us the posterior. The uniform distribution that I just showed is a common example. Imagine, though, for a second that I set up my model so that the parameter of interest was actually the log of what we're calling p. Let's say that's q. If I then set a uniform prior on q, that becomes an exponential prior on p. So which one of those would be an uninformative? It's impossible to say. The point of all this is that priors are an intimate part of Bayesian analysis. There's no getting around using them. And I think a better philosophy is just to embrace the prior, to acknowledge that that's a part of our analysis, and to, if you're worried about your prior, then run your analysis under different prior distributions and see what effect it has on your results.
For this example, for simplicity's sake, we'll use a uniform prior for p. We want to evaluate Bayes' formula to calculate the probability of our hypothesis given our data. In order to do that, we need to consider the three parts of Bayes' formula: the likelihood, the prior, and the probability of the data. The likelihood is the first term. It's the probability of obtaining our k butter side up flips, given p, the probability that each flip will be butter side up, and n, the total number of flips. We discussed this formula in the previous lecture. The prior is our probability of different values for our model parameter p. It's the uniform distribution that we just showed. The probability of the data can be expressed as an integral here. I'm not going to discuss this integral, but if you look in my textbook, you can see a more detailed explanation of this denominator. In general, the probability of the data averaged over all hypotheses is an integral, and often in Bayesian statistics that integral is very difficult or impossible to solve. One way to get around that is using Bayesian MCMC, which I'll talk about in a later lecture. In this particular case, all of the terms in this equation actually simplify to one formula expressed here. That is, we can calculate exactly our posterior distribution if we know the number of flips, our prior on p, and the number of butter side up results. Here we have our prior distribution, which is uniform from 0 to 1 as a dotted line, and the solid black line is our posterior distribution. This represents our belief about the model parameter value given both our prior and the information in the data. You can see two things here. One, the posterior distribution is a lot different from the prior. That is, our data contains quite a lot of information about this model parameter. And two, this posterior distribution has a particular shape and a peak at around 0.6. In other words, our best estimate of the model parameter is around 0.6, and we could use this posterior distribution if we wanted to get a 95% credible interval. That's the Bayesian version of a confidence interval. And again, we can see how the Bayesian approach works in general. We have some prior beliefs, information in our data, modify those prior beliefs, and we have a posterior distribution for our model parameter. Okay, so we can carry out frequentist statistics in the standard way. We can use maximum likelihood approaches, AIC. We can use Bayesian approaches. So how do I decide which framework to use? I have some thoughts on this. As a biologist, it often doesn't matter which framework you choose. If you have good quality data and enough of it to inform your hypothesis, then your results should be consistent across all the different statistical frameworks that we listed. Additionally, in cases where the statistical method that you choose matters, it is almost always true that many other things matter too. For example, the way that you summarize the data, your measurement error, all sorts of little choices that you make along the way. If there's a big difference between a Bayesian result and a maximum likelihood approach, and you can't explain that by some huge difference in the statistics themselves or really, really strong prior information, then it could be a sign that your result is unstable, depends on some details of the analysis, and probably should be questioned. But let's say that we do want to know the pros and cons of the different analyses. Well, if you're using maximum likelihood methods, these methods are fairly standardized and used in a pretty uniform way among different investigators. They also don't require specified priors, and so different researchers carrying out the same analyses will always get the same results. Another advantage to using maximum likelihood in an AIC framework, that is using information theoretic methods, is that when you're comparing AIC scores, what you're assuming is that all of your models are simplifications of some unknown true model. In other words, you don't have to assume that any of your models are true. What you assume is that the different models are approximations of the truth, and you try to choose the model that's the most efficient approximation. By contrast, if you're doing Bayesian model selection, you assume that one of the models that you're comparing is actually the true model, and you're trying to calculate the probability that you've chosen the correct one. This is a different philosophical framework for doing statistics. If, to paraphrase the famous statistical quote, all models are wrong but some are useful, then that might come closer to the philosophy espoused by AIC frameworks. By contrast, Bayesian methods are much better at capturing uncertainty. You can see that uncertainty when we plotted our posterior distributions, but it's also true that a set of Bayesian methods all put together in a sequence can allow you to percolate uncertainty all the way through your analysis. For example, in comparative methods, there might be some uncertainty in your construction of the tree, estimation of tree branch lengths, and with your statistical analysis. And in a Bayesian framework, it's easy to carry the uncertainty of all those different types all the way through your analysis. Bayesian methods also have better computational tools, things like MCMC, reversible jump methods, and lots of different ways to both calculate posterior distributions and compare models to one another. Bayesian methods and Bayesian software is, in general, more flexible than maximum likelihood approaches. It's also an easier computational tool to estimate a posterior distribution than to find the exact peak of a likelihood surface, which is sometimes nearly impossible.
I hope that quick overview is helpful, and the differences among these different methods will become more clear as we get some more examples through the comparative methods course. Thanks.